So I had more than a couple requests last night to push. So if you see my announcement, this homework, I extended this homework until midnight tonight. You're welcome. Thank you for being vocal about it. Because this is a tricky question. But I would like to hear from you all. What specifically gave people issues with this? Where did we get stuck? What? You started it? Okay. This is problem 7. Yeah, it was the last one.
I think this is kind of a matter of figuring out what to do
Okay.
before you start.
And so, it is tricky to kind of figure out what to do. So this dv dt equals r minus, and I think your numbers might be different than mine, but that's fine. So basically, you're trying to solve for this r, which is really the rate at which water is coming in. Because basically, let's break out what's going on in this dv dt. dv dt is equal to r minus 11,700. What does this 11,700 represent? That's the outflow as function of time. And what's the r represent? Yeah, so r, I mean, so hopefully it makes sense why, if I'm looking at the rate of change of volume of water in this tank, I have a positive value r for water coming in at a constant rate, and I have a negative number 11,700 for the water leaking out or coming out of this tank at a constant rate. So inflow. And I care about r, right? That's the thing I want. So don't know enough information right now to solve for r, because I don't really know anything else about dv dt. Is there a way to learn something else about dv dt? So you're pointing at 25 centimeters per minute, right? Is that dv dt? What can I call this thing that we've pointed to? I think dHdt is a very good name for it, because kind of I'm guessing some of you have done this, or maybe whether or not you've actually like written it out. I think H should stand for what? Height. Water. Do we need any other variables? We got V. Anything else? Okay, so those things are not variables, but they are definitely worth knowing something about. Are we okay with the fact that I said they're not variables? 14 meters, and the diameter at top is 7 meters. I don't know how you feel. I hate dealing in diameters if I'm really going to be dealing in radii. So I'll call that 3.5 meters. So yeah, these things are not variables, but I do need that relationship. They're telling you to use geometry of similar triangles. All right, so I got height, I got volume, I got time. Are there other variables I should be looking at? Certainly at least one more that I need to have an idea about, or that I need to be keeping track of. DRDT, what's that stand for? I don't. That would be the rate of change of the radius. But here's the thing, I don't think that's going to be a very easy thing at all to figure out. And I think this might be what's stopping a lot of you, is this trying to get If you have your equation set up, actually know if that's possible, but that's okay because we have ways around that. So the rate of change of radius with respect to time. Do we have a way that relates? So do we know anything else about the volume that we can take a look at? Yeah, I mean, so this is another thing they're kind of hinting that you use. We know that the volume of the water in this tank is going to be equal to 1/3 pi r squared h, right? Just from based on it being a conical shape in the water. So here's what we're going to try to get to. Can we operate on this equation to get to something that looks like dv dt? So you can take a derivative, some derivative of that to give you dv dt, but you also know that that dv dt will equal this, right? So for those of you who are stuck there, that's one thing you'll have to do to bring all these things together. One more hint I'll give you is this. I've already said that this drdt is not something you're probably going to be able to get your hands on. It's certainly not, I don't think it'll be constant. But here's what you can do. Can you rewrite this function v Can I write v in terms of h only? Okay, so I think I'm going to stop there, except to say that we did at least one example last week. I don't think it was this week, but talking about basically leveraging the fact that you have similar triangles here. So this triangle here that I drew, this just represents the empty tank, right? So if the water comes up to here, and let's just use my example. If the height of water is 3 meters, can you use this triangle to tell you what the radius is? Okay. All right. I lied. There's one more hint I'm going to give you. And I need to bring it up because I did a really bad job of representing my height and my volume. What unit should I use for height? Yeah, I heard one vote for meters, one vote for centimeters. Well, what is dHdt given in? Centimeters per minute. So it does not matter what you do, but you have to pick one. Because I'm willing to bet that at least one person here, that was their only problem, the fact that they were dealing with centimeters in one place and meters in another place, which means that the rate you're going to find is you haven't spoken the same language throughout. So it really doesn't matter if you pick centimeters or meters. You just have to be consistent. Oh, never mind. So you want cubic centimeters per minute, right? Also, to illustrate that one more way, how would I convert 11,700 cubic centimeters to cubic meters? Is it as simple as dividing by 100? It's not as simple as divided by 100. You have to divide it by 100 cubed. So, which is totally possible. It's just, I'm highlighting the fact there are a lot of other difficulties that show up trying to get to meters here. Not the least of which is that they don't even want. Nothing went through like this. So I have some questions on this. Really, I don't want to. That way I'm not answering. answer questions. I'm not just answering for your benefit. If you're asking me the same issue. So, I know I haven't seen a lot of people use it. Please don't forget to kind of get us all talking about the same thing. And if people are using Discord, that's another great way to do that. It's just I don't have access to that. Any other questions about this before we get into chapter 3? Well, I think that you should. Well, I think so. I think we're hitting on 2 different issues there. Get all your lengths in terms of centimeters. So yeah, don't call it 14 meters, call it 1400 centimeters or whatever your height is. Also, I don't think you should take a derivative of this until it's in the form of, you can get this volume in terms of height only. You can't usually, but in this case, I know what this cone is shaped like, so you can relate the radius and the height to each other. So we've done some examples like that, but really it does rely on similar triangles. If you want to take pictures of this, go ahead and do it. I will not be able to put this on canvas the way it looks right now. 5, 4, 3, 2. Okay. All right, starting chapter 3. Okay, so starting chapter 3, which is all about inverse functions, and eventually how you deal with derivatives in that context. First, we're going to talk about exponential functions, which I'm going to guess is hopefully something you've seen before. But let's find out. What is an exponential function? What does that mean? Or just what do you think it means? Don't have to be exactly right. I'm kind of just, I want to see. I've heard this term before. But no one's feeling brave and wants to tell me what they think it means. Is this an exponential function? Is this? Ooh. Oh. Is that? Okay. So this one I didn't even tempt you. Let's talk about, actually, let's go for symmetry here. Let's talk about these 2 things. And I think one thing that kind of gets in people's heads is they hear people say, oh, something is growing exponentially, which most people just mean, oh, it's just growing really fast. It's growing and it's increasing at a growing rate, which is not really what exponential means. So those of you who said y equals x cubed is not an exponential function, actually, maybe we'll frame it positively. Why is this exponential, 3 to the x? The exponent's increasing? The exponent, so I heard the exponent is variable. The exponential rate changes. So I feel like I'm hoping I've kind of disabused you of the notion that it doesn't just matter that it gets bigger and bigger. So here's one thing I want to focus on. So if I have x cubed, and 3 to the x, 0, 1, 2, 3, 4, 0, 1, 8, 27, 64, 1, 3, 9, 27, 81. If I look at this column on the far right, how do I get from one term to the next? What's happening? Yeah, multiplying by 3 each time, right? That's what exponential growth means. It's that specific thing. As my input grows by 1, that multiplicative rate of change is going to be constant. Clearly, that's not going on with x cubed, right? I mean, by the fact that I somehow grew from 0 to 1, that already kind of kills the idea that I have any kind of multiplicative ratio going on. So what is an exponential function? It is a function that changes. I don't want to say grows because it could get smaller at a constant multiplicative rate. Actually, that's enough. So a function that changes at a constant multiplicative rate with respect to its input. So are we on board with the fact that x cubed does not fit that? Multiply by 8, multiply by 27 over 8. Included those rates are changing from, even though the step sizes are staying the same. So let's look at some laws of exponential functions. Let's say f of x equals a to the power of x, where a is just some constant. I'm telling you a is a positive constant, and it's not equal to 1. Why do I not want a to be equal to 1? Yeah, that function is not what we care to look at. 1 to the power of x is not. Yeah, it's not really a worthwhile function to look at. If I have a function f of x is equal to a to the x, what's the domain of that function? I got 1 vote for 0 to infinity. So you're saying that x has to be positive. Okay, so you're saying x cannot be negative. Is that okay? So let's say I have 2 to the x. Is f of -2 defined? What is that? Do we think any negative number will work? Yeah. The domain is actually the real numbers. So I'll ask you again, what's the range then? Yeah, so that's 0 to infinity. So yeah, any real number can kind of as you're thinking is so if a is positive, can you raise a to a power and make it 0? The number to a power and make it negative. Also no. So that range is good. And these, I think you've seen these, and probably not going to be thrown by them, but we're going to do something with them later that might be a little more mysterious. If I have a raised to this power x plus y, how do we usually treat this thing? I mean, can I break it apart somehow? Go ahead, Thomas. There you go. And how about the next one? So if we have an additive exponent, we can just break it apart by multiplying the bases. What if those exponents, x minus y, what if they're subtracted? Again, or Sebastian this time. A to the x over ay. Yeah, you tried it again. A to the power of x over a to the power of y. And then finally, a to the x to the y. That's the same as just, I can just multiply those powers together. So again, I'm sure those aren't throwing you. You've been doing that for a long time, but we're going to call back to that before too long. Any questions here? All right. Oh, and then I have a times b to the x. Can I simplify that in any way? Or do I have to keep that parentheses there? Ax bx? Yeah, I don't think you meant that. Yeah, a to the x times b to the x. So yeah, I'm not trying to trick you. 2x? So let's think about going the other way. If I have a to the x, b to the x, can I combine this in any way? Yeah, how come I can't just do ab to the 2x? Like what prevents me from doing that? Not the variables, the bases. Yeah, the bases are unlike. It's the only, so yeah, those first three there, the fact that they operate with the same base is why I can simplify like that. All right, so still sticking with this kind of template of an exponential function, f of x equals a to the x. Let's think about this. Now, let's specifically assume that a is greater than 1. If a is greater than 1, what's that function going to do as x gets really, really, really big? I have a vote for it's also going to go to infinity. Would it help if we looked at an example? Pick your favorite positive number. 3. Okay, 3 sounds good. As x gets really, really big and I raise 3 to really, really big powers, is that going to continue to grow? What's going to happen is x gets really, really small. Okay, yep, it's going to approach 0. Because think about it this way, let's just do f of negative 1,000 equals 3 to the negative 1,000. What's probably a more digestible way to write that? So clearly 3 to the power of 1,000 is going to be a massive number. Your calculator probably couldn't even help you with. Yeah, dividing by 1 by that's going to be very, very small. A small positive number. And just a refresher, can we ever achieve 0? No. So the limit is 0, but I can't ever reach it. All right, how about if a is between 0 and 1? Then what is the function going to do as the closer to 0, right? And just think about what happens to, like, I wrote down 1/3, but really any fraction or any number less than 1 will work. But what's going to happen to 1/3 if you square it or if you cube it and so on? On the other hand, what's going to happen if I make x really, really small and I approach infinity? So again, if I use some large number here, negative 1,000, it's going to be 1/3 to the negative 1,000, which is going to be equal to the power of 1,000, which is huge. How are we feeling about this? I can. All right. So let's look at a specific function here. I have the limit as x approaches infinity of this, not technically an exponential function, but it is based on one. So think about the way we've dealt with limits in the past. How can we think about this one? Can I look at these separately? Why am I allowed to look at them separately? So yes, because the limit laws, but one thing I want to be sure of is, because this can be lost. Why am I allowed to use all those limit laws that we went over in the past? For example, if I had the limit as x approaches infinity of 2 to the x minus 1, I could not use the limit laws here. So why am I allowed to use them for this example, but not this other one that I just came up with? Because what? That does have something to do with it, but I'm looking for something more fundamental than that. For us to use those limit laws, if I want to split things up like this, then I have to have the individual limits that I'm breaking it up into have to exist. So if I look at the one that I just came up with, right, so that limit doesn't exist. So because of that, I'm not allowed to use those limit laws to break that up. As opposed to this, what is the limit as x approaches infinity of 2 to the negative x? 0. Do we understand why that is? Is there a way to rewrite 2 to the negative x? Yeah, that's the same as this, 1/2 to the power of x. Which, we didn't really talk, just now we didn't really talk about what happens as x goes to infinity or negative infinity for a function raised to the power of negative x. But you can always rewrite. I think for all of us, me included, it's just more natural to think about the exponent when it's positive. So yeah, don't forget that you can rewrite that way. And this other limit, what's this other limit? Yeah, it's a constant, so nothing changes. So this limit is -1, right? So let's use that to sketch something of a graph. So we said the limit is -1. So I'm going to have a dashed line here for y equals -1. And you said that as x gets really, really large, this limit approaches -1, right? So I know that as I go far to the right, I'm going to have this tail that kind of does this. Let's think about what's going to happen before that. Where is this going to cross the y-axis? Or to vote for 0? We okay with that? What's 2 to the power of 0? 1. So 1 minus 1. Yeah, I agree with that then. So it crosses to the origin. So it's going to look something like that. And what's going to happen as x gets really, really small? As x gets these, as x, basically as I go to the left of the y-axis, what's this function going to do? We go towards infinity. And this is basically the behavior that, exponential functions will do one of two things as x gets really, really large. They'll either decay to some value or they'll grow infinitely or arbitrarily large. Any questions here? Has anyone ever seen this limit before? I'll ask you to write it down. There's another way where you might, another like look at this you might have seen. The limit as x approaches 0 of 1 plus x, the 1 over x. And hopefully you can see these are equivalent ideas. So basically what you have is this. You have x is getting larger and larger and larger, right? Inside the parentheses, it's going to decrease to what? Like get closer and closer to what? To 1, right? So you're right, 1 over x will get closer and closer to 0. But yeah, the bracket will get closer and closer to 1, right? So as x gets really, really large, the expression inside the bracket is going to get closer to 1. And so basically what I'm doing is, as x gets really, really large, I'm taking a number that's getting really, really close to 1 and raising it to a power that's getting really, really, really large. So what do you think that's going to end up doing? So what happens when you raise 1 to any power, no matter how large? Equals 1, right? What happens when you raise any number larger than 1? The larger and larger powers. It gets larger and larger and larger, right? So this limit is actually, it doesn't do either one of those things. This limit comes out to this number that's kind of, maybe you'll recognize it as 2.71828. Both of these are going to do this. Has anyone seen this number before? That's E. So this limit right here, the limit as x goes to infinity of 1 plus 1 over x to the power of x equals E. That's where that number comes from this this limit operator on this expression. Jordan? No. That one is supposed to be x to 0. So let's think about this one. No, but and really, to be complete, I really should do this. 0 from the right. X approaches 0 from the right, that 1 over x is arbitrarily. So I just wrote them both because we might use both depending on the situation, but really both are out there. Neither one of these things is universally accepted over the other. But we've all seen the number E before, right? Okay. So yeah, this is where it came from. This is how we discovered it. So let's do this here. Let's find the limit as x approaches 0 from the left of e to the 1 over x. What do we think that's going to be? And if we want, we just we can kind of think about, what's the first way we dealt with, or what's the first kind of approach we took in looking at limits? Yeah, we can just guess a few things and hope something jumps out at us. So let's do that. What are some good numbers to try? -1, -2. Could do -2, but if I already started at -1, -0.5, and then I'm gonna I'll do one more. And then I really should do the positive versions of all those, right? Good catch, Alan. So I can just look at those, and this first one's going to be just E, right? Oh, no, 1 over E, which is not something I have memorized. Should 0.368, that looks familiar. So 0.368. How about next one's going to be e to the negative 2, right? So 0.135. Are we already kind of getting an idea? The final output should not be negative. And I'm only going to write one more of these down because hopefully it's becoming evident what's happening. What do we think the limit is? 0. Does that make sense? So basically what's happening is I'm plugging in very, very small negative numbers for x, right? And then when I take the reciprocals of those very small negative numbers, they become very large. Or like, let me rephrase. They become negative numbers that have very large magnitudes, right? So yeah, I think I agree with 0. Any questions on that? Because I should go back while I'm asking that. We okay here? All right, and let's put one more. The limit is x goes to infinity of e to the 2x over e to the 2x plus 1. And I use the limit laws to break this up. Got to vote for yes. I think the same person voted for no. You were right at least one of those times. Anybody else?
Yes, because
Well, let's look at it in individual terms here. Let's just think about each. Can I do something to this that will allow us to use the limit laws? And as I ask that, think about this. You know, we've done things like this in the past. There's some algebraic manipulation we can do to this where we can then bring in our limit laws. Go ahead. Can't take it out. And you know what, I definitely bear some blame for this because I think I had you all think about it like this, but one thing I want to get us in the habit of is this. If I multiply top and bottom by 1 over x squared, think about what this becomes. It's the limit as x approaches infinity of 1 plus 3 over x squared over 2 minus 1 over x squared. Now I have 4 different terms, right? Do all of those limits exist as x goes to infinity? So the 2 are constants, those clearly do. And the other ones go to what? Yeah, so now I can just go 1 plus 0 over 2 minus 0. So when I have all these different individual terms going, but if I somehow each other, I was just using a parallel. I think one thing I could introduce to this x, or equivalently e to the negative 2x over e to the negative 2x. What is e to the 2x times e to the negative 2x? Not 0. It's e to the 0, which is 1. Maybe I'll write that like that first. E to the 0 over e to the 0 plus e to the negative 2x. So 1 over 1 plus 1 over e to the 2x. Now are limit laws available to me? Constant 1, constant 1. What does 1 over e to the 2x go to? 0. Yes, I agree the limit's 1. How are we feeling? Any questions on that? Okay. Short section. So I want to jump into 3-2. I think I can get a little bit of 3-2. Yeah, let's at least talk about this. So inverse functions. What is an inverse function? So it undoes. So yeah, in target cursor. Nope. There you go. No, that's the wrong slide. So what is an inverse function? It undoes some other function. So yeah, so we'll say it this way. Let's say this is true. Let's say this, I have a function and that some point on this function f of 2 equals 9. Can I say anything about this inverse? Based on that piece of information, can I say anything at all about the inverse? Go ahead. Do we agree with that? So that's one thing that makes an inverse function actually an inverse function, is basically a function is something that where I have a domain set of numbers and all of those numbers in the domain are mapped to something in the range. All the inverse function does is basically it turns that mapping around. The range set becomes the domain set and vice versa. So that's one thing I'll say here. It's swaps the domain and range sets. Any other thoughts you have about what inverse functions are? What kinds of functions have inverse? Okay. Newest functions, maybe? You draw a picture here. Does this function have an inverse? Okay, I got to vote for yes for this. How about if I write this? F of x equals x squared. Got to vote for no. We're going to vote for yes.
Well,
What doesn't pass the vertical line test? The inverse would not, right? So this one does not. So one thing I want to point out here, and I try to get it out of here. Those functions that, so the vertical line test is just that's what we use to test for what, whether it's a function, right? So the mathematical definition of a function is if I take one thing from a domain, then it either maps to one thing in the range or to nothing. It can't map to multiple things in the range. That's really what the vertical line test is looking at. That other test is, so we all agreed that this graph I drew has an inverse, right? Why don't I graph what y equals x squared looks like, or something close to it? That you said does not have an inverse, right? Why not? Do you remember why? Yeah, the inverse would be flip on its side, right? If you kind of imagine what that graph looks like. But the answer I'm looking for here is the kind of functions that have inverses are called one-to-one. Does that sound familiar? Yeah. So basically, let's talk about what the definition of a function is. For a function, it's one-to-one. There's one. I think a lot of that somewhere else. How many? Okay. Function, right? But here's the thing, just to kind of f of x equals x squared. We just agreed that does not have an inverse, right? But doesn't it? Isn't there? Isn't there? So let's go back to Cameron's language here. Undoing another function. Isn't there some function that undoes x squared? What is that function? Square root of x, right? So I'm going to just say this. So let's go back to my definition. It's one-to-one if everything in the range only gets one thing from the domain that maps to it. So this is what we usually do when we talk about the inverse of the squaring function. We just cut the domain in half. So that's still f of x equals x squared, right? But now I'm saying this is true. X is greater than or equal to 0. Is that thing, the way I've restricted it and redefined it, is that one-to-one? So I definitely have an inverse now. So that's why, I mean, things like x squared, which, you know in your heart has an inverse. I know what the inverse of squaring is. That's when it exists, when I'm able to, basically I'm cutting things out of the domain so I can make an inverse exist. All right, we'll pick up from there on Friday. So tonight I'm going to post the